All right, let's just get started. First of all, thank you for joining the session. And so we have the QR code for our GitHub repo, as well as our documentation websites. And there's also a YouTube channel with only 2 videos so far. So if you really like the talk and you want to make contributions or have your use cases, feel free to go GitHub repo, open up issues. If you can make contributions, you are welcome to do so. And if you really like our projects and want to keep it on your agenda, give us a GitHub star. Right. So let's just get started. So the idea is intelligent LLM routing within the Kubernetes. So what we are discussing at the moment, we are submitting the talk. We have not finalized the project yet, but we open sourced the project 2 months ago on end of LLM projects. And ever since then, it's get a lot of attention. So we probably need to change the topic, but it's all about the project itself. So what's the use cases we are talking about? So if you are familiar with how you are using the OpenAI kind of a schema for interacting with large language models, you have to be really careful what you're going to use for parameters. This just reminds us of the good old days of assembly language. You know every bit about your register, your bus line, and your the detailed memory management. This is the same case as you are using the OpenAI API for language model inference kind of service. You have to know which model you're going to use, especially when you are using the VLM ecosystem. There's so many hundreds of models available to use. You have to know whether you want to turn on the reasoning mode or not. The worst case is there's 3 reasoning, light, medium, and heavy. You have to turn it on for specific purposes. And potentially, you also want to pick up the pricing tiers. Even for OpenAI, there's a 4.0, 4 mini, 5, and there are 5 things. So many models you want to choose. How do you know which model is the best for your workloads with cost effectiveness? So that is one of the top questions many of the developers are facing. So we want to make this experience smoother. Use the same line of assembly language. So we want to be the compiler for your inference experience. So you do not have to know exactly how to use your register, how to use your memory bus. You just need to know the prompt. And we are going to figure out the rest of the details for you. So this talk is about how this magic happens in the background. We use models for extensive developments for classification and summarization, and also for jailbreaking. So this is more than just programming. There's a model inside and a model for the model service. So this is the core value as we are providing to the ecosystem. It's really as an open source democracy for advanced AI gateway features. So if you follow the industry news carefully, you will notice that GPT-5 is not a single model. It's a unified framework for lots of services. They have a real-time router to make a decision, intelligence decision, which models they're going to use for your inference request. OpenAI did not disclose more than that details. So we are trying to make the democracy available for all the open source ecosystems by providing robust and rich features that everybody can use out of the box. And we want to get rid of this detailed, sometimes tedious information that you have to choose during the inference experience. So what we use is in 3 ways. That's what we are using classification, and then we are using the model caching, semantic cache, and integrated with PRI and the jailbreaking detectors. So let's go each one of those information in detail. So for classification, so if you are working with machine learning and NLP, this is the classic type of workloads that people will use. Giving me a prompt, tell me what kind of a complexity this prompt is and what kind of a specialty this prompt requires. And that will just help us pick up the right models for you. So if this is a prompt that's designed for math, then we choose the math specialty models. And then if the prompt is aimed for creative writing, then we potentially pick up the more suitable models for you. So this kind of matching is done internally by classification. But what we do differently than simple classification is that we use the more robust approaches, incorporating latest technologies in NLP. So we aim for two kinds of personas: people who are using CPU for extensive deployments, and people who are using GPU for more advanced classifications. For GPU, we are using the BERT family. That is encoder-only models CPU can handle very effectively. But if you're using the decoder-only, like the Quan and some other models, then we have to rely on GPU. So we fine-tune both GPU and CPU models for different classification capabilities. So you know the differences between the decoder and encoders, not just on CPU and deep GPU, and also the latest, like a context window length, the versatilities, that also matters a lot. But we are trying to catch up these differences under the hood by providing you the choice that we are facing into your environment. We do not just stop over there. We also use the embedded models for classification. So if you are using, going to one step further, so if you are using something like a RAG, retrieval augmented generation, you know how this embedded model works. So we also use similar ideas using the embedded models for classification in our repository. So you can just using Quant3 embedded models to classify what kind of workloads you want to use and what kind of models you want to fit into that workload. So this is how we do for classification. With the classification done, then you come to the model itself. If you are using the reasoning model, like the model can think and give you a more extensive tokens and gets you the better results. So that's the thinking models. And if you do not want to use the thinking models, you want the quick answers, then you potentially will sacrifice the accuracy in trade-off the latency. So we figured out that not all the workloads need reasoning in two ways. One is that the token is expensive. You pay for the token as well. You pay for the token for accuracy. And you may not get the accuracy that really matters. If you are just asking something trivial or something that's even non-reasoning mode can work well, then you can just turn the reasoning off. So that's why we just benchmark the models, and then we figured out what's the model's what's the model's advantage when turning on reasoning. And we fit that profile into the prompts that you are providing, and then we automatically enable and disable reasonings on that behalf. So just to give you one example, we figured out that GPT OSS models are really good on reasoning on STEM kinds of categories like math and coding, but it does not give you advantages when you are really doing like creative writings, legal or something like that, factual based workloads. So we turn off the reasoning for this kind of workloads once we classify what kind of prompts you are using. Right. So that's how we do the model selection and model configuration. And then we also do the semantic caching. So if you're already using these features, you know this perfectly well. So many of the prompts sound very familiar, but if you just do word-by-word matching, they don't match to each other. One of the very simple use cases that people can ask the same question in two different languages. Let us say, how many people in Atlanta? In English, and you can also ask the same question in Chinese or in French, in many other languages. If you are just by reject kind of a word-by-word matching, you will not find this match. But if you are just turning on this similarity match using embedding models, then you can exactly figure out these are the same question, and I can just use the cached copy instead of regenerate the results from the models. So this was what the semantic caching is about. And we found out this is greatly reduced the cost as well as the latency. The next one is the model protection. So this is more for the jailbreaking. If you are using, like, say, Gmail for mail service, you will figure out Gmail has a lot of spam filters. If something identified as spam, then you just stop it from getting into your inbox. This is the same idea of jailbreaking in large language models. Some people want to break the guarding system in language models by providing tricks. The tricks could either trick the models to tell something that it should not tell, or just provide denial of service to the models to let the model just collapse by itself. So this kind of jailbreaking can be detected by the router. So we are using a number of jailbreaking detectors. We have some fine-tuned models. We also adopt open source models like a Quant 3 Guard, which got released 2 months ago. And we also opened up a new, this is a refactoring undergoing. We want to have a broader support for people who are using specialized fine-tuned models of yourself. Just bring your own models. So we are trying to support this scenario as well. And then very lastly, so because this is a CNCF project, this is a CNCF ecosystem project. We're using Envoy XProg extensively. And one of the tricks in Envoy is that most of the projects in Envoy is written in Golang. And for certain reasons, Golang does not have a great ecosystem on machine learning. So we write the machine learning layers, how the models work with each other, with our source code in Rust. And then we're providing the foreign function interface for Golang, so Golang can use these functions without having to re-engineer the machine learning layers underneath. So we can provide the scalability and integration opportunities for all the ecosystem that's using the Rust core. So this is the project link. Just give us a heads up if you like something to happen. If you like something to make contributions, this is the way to go. Right, a little bit into the architecture itself. So we use, as I said, we use extensively using machine learning for many of the functionalities and providing this high-level logics based on the machine learning's output. Right, so because this is really a router is focused on the efficiency and the scalability. So we spend a lot of time engineering how we can improve the efficiencies in 3 ways. One is the reduce the model inference latency. So because we have so many classification work to do, we classify the prompts, we classify the PII, personal identification information, we classify the jailbreaking. So there's so many classification needs to be done. We're using LoRa-based adapters. So you're using the same base model, and then once we classify the base model, we go into different LoRa adapters. So instead of O times 3, we do it linearly. We only do it once. So that kind of savings is very impressive. The second is that we are using a lot of ideas we got from VLM itself, like continuous batching. Right? So VLM benefits greatly from continuous batching as well as page attention. So continuous batching is one of the ideas that we are, as one of the batch job finishes, we immediately inject yet another batch job. So we can keep the pipeline full without have to wait and see. So this improves our classification efficiencies by 10 times. In both the generative classification as well as the embedding based classification. We are using the Candle framework from Hugging Face. This is really a great framework you should take a look at. It's being actively developed by Hugging Face folks. So it's Rust-based. That gives us a lot of head starts in the beginning. And then we also improved upon the Hugging Face base source code by adding the scalability layers on top. So we can just run this classification as efficient as we can without have to spend too many time to in the latency layer. And then once this Rust core machine learning libraries integrated with the XProg Golang-based code base, it can be extended to other projects as well. So if you look at, if you read our documentation, you can find out we have a lot of integrations with existing Envoy-based projects, like Envoy AI Gateway, Kubernetes Gateway, inference extension, and also LLMD projects. I think that's just to name a few. So this is really our core competence. We are really put great values on efficiency and ecosystem integration. All right, a little bit on the functionality and the integration itself. For semantic cache, I just mentioned, for similar queries, you get same response. We support in-memory, also the Milverse, which is the persistent store or vector persistent storage. And we also have our innovative in-memory indexing plus remote storage, kind of a hybrid architecture to reduce the latency by even by yet another magnitude on many of the workloads. We support a lot of integrated with a lot of existing Envoy-based gateways, LLMD, Kubernetes Gateway API extension, Envoy AI Gateway, just to name a few. And we support a lot of CNCF native observability stack, Prometheus, OpenTelemetry. So the nice thing with the OpenTelemetry is that we can provide the end-to-end tracing. So if you issue a query from your application, you can piggyback all these spans to the routing layer. And I think somebody also interested in to get, extend this span to the VLM layer. So you can get end-to-end analysis of what is going on from tracing sources, who is doing what, and how much time spent at what stage. That will give you a visual representation of diagnosis you can further use to optimize for your optimization. For user experience, we have the integrated open web UI and also the Hugging chat from Hugging Face. We are going to run a very quick demo to see how our dashboard looks like. It's really cool. For the rest of the presentation, it comes from my coworker, Chen. So Chen is not able to join the meeting on stage. So he has recorded sessions to cover the rest of the talk. So because this is really for the emerging and research track, we focus very much on the innovation and the benchmarking results. It's more like a research presentations from this point on. Let me just play it.
Hello everyone, at KubeCon, I'm Chen Wang from IBM Research. It's such a pity.
Actually, let me use this. Sorry. This is actually better.
Hello everyone, at KubeCon, I'm Chen Wang from IBM Research. It's such a pity to miss all of you this time, as I unfortunately twisted my ankle recently. But I'm glad to share with you our new project, VLM Semantic Router. I will basically introduce some real-world use cases for both the semantic routing and the semantic caching, and some evaluation experiments we have been doing to share with you a brief view about how VLM Semantic Router can benefit in your environment and for your workload. So we all know that running in production large language model workload is very expensive. But what if I told you that a significant portion of that cost is due to 3 critical inefficiencies? So we are talking about the first, misrouting to a very large or complex model. Second, over-provisioning in terms of reasoning, where you have a long system prompt when your question is very simple. And third, semantic redundancies. So you may have similar queries sending again and again. So these issues waste the GPU resources and actually inflate your cloud and API bill. And our analysis of production traces confirms this. So we see that 28% of queries repeat within a short window, which is a huge opportunity for caching, and 31% of requests could skip complex reasoning with no loss in quality. So this means we are burning tokens and GPU cycles unnecessarily. So our solution, cost-aware semantic caching and routing in VLM Semantic Router, address this with 2 components. A lightweight semantic router for intelligent model selection and reasoning chain selection. And second, a category-aware hybrid semantic caching for reusing responses. So we place this system gateway inline, so this can minimize latency and ensures we only hit the expensive backends when absolutely necessary. So this intelligent control is how we drive down cost while maintaining performance. And let's dive into some concrete numbers to show how it works. So the core of our approach is a semantic router, which routes the request based on its complexity to a properly sized model endpoint or a properly reasoning chain. So, and the results are compiling. So we tested on the MMLU Pro benchmark, we show the link here, which covers 14 diverse categories from topics from law to computer science. So the router's auto selection mode achieved around 64.3% aggregate accuracy. Now look at the model pool we used. We have Gamma 27 billion model, Mistral small model, and Pi 4 model, each with different strengths and weakness. So the best single model Gamma only hit around 57.1 accuracy if we use that deployment alone. So by intelligently matching the query to the right-sized model, the router delivered around 6.8 to 15.7 percentage point improvement over any single model deployment. So this is a huge jump in terms of quality. It proves that a heterogeneous model pool managed by an intelligent router is superior to simply deploying one large general purpose model deployment. But the best part is that this quality improvement comes with a massive cost saving. So how does better accuracy actually translate into lower cost? It's simple. We're using the right tool for the job. We're not sending a simple query to the most expensive model. Our intelligent selection delivers an estimated 39.5 average cost reduction. And looking at the traffic distribution, the router sends 40% of traffic to Gamma, 35 to Mistral, and 25 to Pi 4. This distribution is based on the query's characteristic, not just a random split. This intelligent selection reduces our average cost to about 60% of the base cost, while improving the accuracy at the same time. So the key takeaway here is that cost and quality are not a zero-sum game when you introduce semantic control at the routing layer. So by optimizing the model selection, we achieve both efficiency and accuracy gains simultaneously. So this is the power to move control to the routing layer. Now let's take a look at how we achieve this routing decision with minimum latency. So for the router to work, it has to be fast. We can't introduce routing overhead that negates the cost saving. Our LoRa-based router is designed for gateway inline deployment, running on cheap GPUs like L40. We use a lightweight fine-tuned Quan 0.6 billion model with LoRa adapters. For the routing to different reasoning chain, we also fine-tune a modern BERT model which can also run on CPU. So this allows us to classify the query along 4 different dimensions. Whether it needs the reasoning or not, what's the intent of the query, what's the complexity and density of the query. And this classified in a single fast forward pass. So the performance is also very nice. We can achieve around sub 20 milliseconds, 99 percentile routing latency. And we also implemented some continuous batching solution for those queries that needs to run on, for example, L4 GPU. And on L4 GPU, we can sustain 86.7 queries per second for classifications of routing queries on L4 GPU. So our Rust implementation is also a huge factor here. So our Rust implementation is actually 3.2 times faster than a Python equivalent. So we also validated the value of the learned classification. So our 78.4 accuracy is a massive 20.3 percentage point improvement over a simple query length heuristic. Right? It also beats the zero-shot in-context large language model classification by 18.4 points, and those comes from fine-tuning. So this validates that the task-specific LoRa fine-tuning or full-parameter BERT fine-tuning is essential for high-performance, accurate routing with efficiency. So now let's take a look at the other half of the equation, which is the semantic caching. The semantic cache is a second component, but it actually runs first before the router. So all its architecture is designed for speed. We use a hybrid approach that separates the fast local search from the slowest remote storage. So the key is the in-memory HNSW index. So this index holds compact embeddings and keys, allowing for microsecond to millisecond searches. Only on a validated hit, we do fetch the full response payload from an external storage. So this split is critical. It can reduce the average cache miss penalty from about 30 milliseconds, which is typical for a client-server mode vector DB, down to only 2 milliseconds for our local in-memory lookup. So that's a 15 times speed up. So this performance gain fundamentally changed the economics of caching. So by reducing the miss penalty from 30 milliseconds down to 2 milliseconds, we lower the break-even hit rate to about 1%. So this is 15 times reduction in the required hit rate for economic viability of caching. So now categories with only a 6 or 12% hit rate, like those specialized legal or medical queries, become net positive for caching. We then use category-aware policies to fine-tune this. For example, code generation needs a very tight similarity threshold. We can set it high as 0.9 to avoid false positive. But for conversational chat, we can use a looser 0.75 to catch paraphrases. So we also adapt the time to leave based on the content's freshness needs. So this fine-grained control ensures we get a positive return across all query categories, not just the high-frequency ones. So how does a request actually move through the system? Let's work through the workflow. So the core principle of our design is always cache first. We want to avoid touching the GPU or even invoking the router, semantic router, unless absolutely necessary. So when a query hits the gateway, we first extract its category configuration. This tells us which embedding model and which category-specific similarity threshold to use. Next, we embed the query, performs an HNSW search in memory. That's the first pass. If we get a cache hit, we quickly validate the time to leave, fetch the full response payload from external storage, and return the cached results in about 2 milliseconds. So that's a massive win for latency. Only on a cache miss, we do invoke the semantic router. The router core, written in Rust, then performs classification using our lightweight Kendo inference engine with our fine-tuned BERT models or Qwen3 models with LoRa adapters. So the cache first design minimizes the latency and resource usage by making the fastest decision first. Now let's look at what happens when we miss the cache and move into the routing phase. So when the cache misses, the request moves into the second half of the flow, the semantic routing. So the router's output drives a cost-aware endpoint or reasoning chain selection, choosing the most efficient model from our VLM pool or choosing the most reasoning chain with different system prompts. So the selected model then generates the response. Crucially, here the response is then admitted back into the cache under the profile emitted by the router. So this ensures the cache learns from the router's decision. So our implementation for the router is a Go-Rust hybrid integration. So the Go interceptor handles the high-level HTTP gateway integration. The Rust router core provides a low-latency, high-performance classification using a Kendo inference engine. We also have a continuous batching implemented in Rust for serving large models like Qwen3 for high throughput. And in the future, we will support more like guardrail models as well for AI safety purpose. All forwarded requests are OpenAI compatible, so it can directly connect to different backend inference stack, such as LLM from IBM or raw VLM deployment. This stack achieves less than 5% end-to-end overhead with zero copy data transfer, making it production ready as an Envoy extension prop filter or a standalone Go interceptor. But why did we build this complex system in the first place? It all comes down to the production inference workload inefficiency we observed from our traces. So our trace analysis from production VLM deployment revealed two major areas of waste. We mentioned that earlier. First, 28% of queries repeat within a 10-minute window. These are things like FAQ chat, boilerplate code generation, and templated analytics. So this is pure waste if you're not caching. Second, 31% of queries could skip complex reasoning steps with no loss in accuracy. This means we are burning tokens or GPU cycles on unnecessary long, complex chain of thought reasoning for simple tasks. And then the third part is we also unnecessarily route the query to a very large model, right? When the query is also simple. So combined, at least 59% of our traffic can benefit from either reuse or right-sizing the model's reasoning chain to router. Look at the impact on time to first token, TTFT. A cache hit returns the result in about 52 milliseconds. A cache miss, which may involve routing and model inference, right, takes over 800 milliseconds. So that's a 16 times difference in user experience. As model continues to grow exponentially, these semantic inefficiencies become critical cost drivers. So the data is the foundation for our entire approach. If we can fix those problems, repetition and unnecessary reasoning or unnecessary large models, we can unlock massive efficiency gains. So that's all the data and experiments I would like to share today. Thank you all. I will hand it back to Huamin.
Right, I think that's it. We have come to the end of the session. So if we have a small demo to run on YouTube. So we also can open up a Q&A while we are watching the YouTube for our dashboard. So if you have questions, feel free to raise your hands and while we are watching this video. So this is basically our dashboard.
Hi, thank you.
Thank you.
Hi, thank you. That was a great talk. I'm a Rust person. So I'm curious about the choice to FFI and to Go versus using Tonic or gRPC library in Rust. Is there a reason to wrap Rust core in a Go layer versus just using gRPC directly?
gRPC there's a latency over there. We do not want to manage latency. And the other thing is function call. We can make a lot of optimizations. Just for example, the continuous batching that we are using is continuously running in our code. So you know which API you're going to call. gRPC, there's a possibility that's accountable for milliseconds latency is still not something we want to build up.
Yeah, but specifically versus just why not implement a gRPC server in the Rust component directly?
This for ecosystem.
Okay.
People who are using the extra block are mostly realize everything in Golang.
Okay.
In principle, you can,
Okay.
but just for the people who have more experience with Golang. Yeah.
That makes total sense. Just
Yeah,
curious about that.
Right. All right.
Hi, I just had a question about, so there was this slide about production workload analysis where there was like a 28% query repetition between like FAQ, customer queries. Is that for just
So we are using some of the workload space that's for evaluation.
Yeah.
Obviously, this is really a case by case and customer by customer situation. So, but on the spaces we are using, we see that it's a kind of a reduction we can achieve.
So is that like single-turn chart? Because I'm thinking for multi-turn chart application, the semantic hit would be really rare.
Single shots. I think you have points over there, but I think right now, if you just switch over to the response API, you can identify single and multi from those points. There's still a possibility you can identify the single shots out of the multi-turn conversations.
How do you do that? Could you repeat that?
Just if you are using the response API, because response API have a tracking, which is the conversation happened before and which is the new conversation. So you can still extract the latest, the current conversation out of the multi-turn conversation.
So in the multi-turn conversations, have you observed semantic caching still?
We have not gone to that stage yet. We are still building the response API support at the moment.
For single, okay.
Yeah, but for single shots, single turn conversation,
Makes
that's
sense.
the something we observe.
Makes sense.
Yeah.
Thank you.
Yeah, thank you.
Just want to say thank you. This is very cool to see open source.
Thank you.
And would love to contribute. I noticed you're using the MMLU pro data set for the evaluation. Have you tried any other domain data sets to evaluate and see any strengths or domains
that's
that highlight?
What is not shown in the, so we actually have a range of data sets evaluated. So LMU is just one of those. We're using ARC, Common Sense QA, GPQA, HealthSwag, and Truthful QA. So across the board, when we turn on and turn off the reasoning mode, we see quite some differences. But across the board, auto selects the reasoning mode. We see, we beat everything in that space. Yeah.
Great, thank you.
Yeah, you can also find our publications online. So if you're, there are somehow on preprints, but you can find the information over there to see what the details we are using. Yeah.
Thank you.
All right, thank you for attending. And again, just go to our GitHub for issues and comments. Thank you.